Okay, here we are at the last video of the week and the very last lecture video for the whole course. So in this last video, we're going to put together what we learned in the first two videos this week and learn about the relationship between work and energy, and we'll finish off by learning about power. The definitions of work and energy indicate that some sort of relationship exists between them. And just as a reminder, in the last video, we defined energy as the capacity to do work. And in the first video, we defined work as the means by which energy is transferred from one object or system to another. And the unit of measurement for work and energy is joules. It's the same for each. So this is another indication that work and energy are related. All right, so let's figure out how they're related now. Remember that weightlifter example that I used in the first video, where during the raising part of the exercise, the barbell was raised 70 centimeters or 0.7 meters, and the work done by the lifter was 700 joules, remember? Going from this position to this position. Now, how much more energy did the barbell have after it was lifted? Well, it didn't have any more kinetic energy because it wasn't moving before the lift and it wasn't moving at the end of the lift. But its potential gravitational energy changed because it changed heights. So let's figure out that change in potential energy. Okay, so the change in potential energy is the difference between the final potential energy and the initial potential energy. So that's this first line here. Change in potential energy. The weight of the barbell doesn't change, so we can rearrange that equation a little bit and we fill in our numbers. We end up with a change in potential energy of 700 joules, which is the same if you remember the work done in that raising phase was also 700 joules. So perhaps work done causes a change in potential energy, or maybe work causes a change in total mechanical energy. In the discus throwing example we looked at, also in the first video, a discus thrower exerted an average force of 1,000 newtons against the discus while the discus moved through a displacement of 0.6 meters in that same direction of the force. And we calculated that the work done by the thrower was 600 joules. Now let's assume that the force exerted by the thrower was constant and the displacement was horizontal. If work does cause a change in total mechanical energy, then the work done by the thrower on the discus would cause a change in the energy of the discus. Because the displacement of the discus was horizontal, there was no change in gravitational potential energy. So the work done by the thrower caused only a change in kinetic energy this time. So the mass of the discus is 2 kilograms. So M is 2 kilograms. And knowing that the work done was 600 joules and that the initial velocity of the discus was 0, we can determine the velocity of the discus at the end of the period of work. So we know that work is related to energy. And this equation here states exactly that. Work, so U, is equal to the change in kinetic energy plus the change in potential energy plus the change in strain energy. So in this example, the displacement of the discus is horizontal, so there's no change in potential energy, and there's also no change in strain energy. So in this case, in this example, work is equal to the change in kinetic energy. So if we replace the formula for kinetic energy, we get that work is equal to 600 joules, which we calculated. That's equal to 1/2 of mass times the final velocity squared. So if we just plug in our numbers in the equation and we isolate for that final velocity, we obtain a value of 24.5 meters per second according to this work energy principle or relationship. Could we have found the final velocity of the discus with Newton's laws of motion? With the same information, we could have obtained the final velocity, but it would have required us to do 3 lengthy calculations before we could even solve for the final velocity. First, we'd have to do F equals ma to solve for the acceleration. And then with the acceleration, we would be able to do acceleration is equal to change in velocity over change in time to find the time. And then finally, we'd be able to do v equals displacement over time to solve for the final velocity. So we finally made it to our exact same final velocity calculation or value, but it took us a lot more steps. So it's the same result that we got using the work energy principle, but it took a lot more effort, if you will, by using Newton's laws of motion. So there's no need to focus too much on this slide when you're studying. It's more just to show you that there is a link between what we learned in the previous videos and what we're learning this week. But now we know the work energy principle, so there are simpler equations that we can use. So the examples of the bench press and the discus throw demonstrate this work energy principle. So the work done by the external forces acting on an object causes a change in energy of the object. So mathematically, that relationship, which we saw in the previous slide, is shown as U, so work, is equal to delta kinetic energy, so change in kinetic energy plus change in potential energy plus a change in strain energy. And all of this combined is a change in mechanical energy. So work is equal to change in mechanical energy. In sports and in human movements, we're often concerned with changing the velocity of an object because changing velocity means changing kinetic energy, and the work energy principle shows how kinetic energy can be changed by doing work. So more work is done, and so a greater change in energy occurs if the average force exerted is large or if the displacement is in line with this force and that displacement is long. So this sounds super similar to the impulse momentum relationship that we learned in the previous week of videos, so in week 9. Using the impulse momentum relationship as the basis for technique analysis, the creation of a large change in velocity requires that a large force be applied over a long time. Right? That would be this side of the equation here. The work energy principle indicates that the production of a large change in kinetic energy, and so a large change in velocity, requires application of a large force over a long distance. And that's just breaking down work here. So let's think about throwing a ball. If you throw only with your wrist, you're able to exert a force on the ball through a small displacement, right? Your wrist isn't moving that far. The work done is small, and as a result, the ball's change in kinetic energy is also small. The ball's velocity when it leaves your hand is small. If the wrist and the elbow are involved in throwing, then you're able to exert a force on the ball through a larger displacement, which means that the work done on the ball is larger, and as a result, the ball's change in kinetic energy is also larger. So that means the ball's velocity when it leaves your hand is faster. So this is all related. The work energy principle can also be used to explain the techniques that are used in transferring or absorbing energy from an object. When you catch the ball, its kinetic energy is reduced or it's absorbed by the negative work that you do on it. Similarly, your muscles do negative work on your limbs and absorb their energy when you land from a jump or when you fall. The average force that you must exert to absorb the energy in catching a ball or in landing from a jump or a fall, it depends on how much energy must be absorbed and over how long a distance you can apply that force. If that force is too great, then it may injure you. You attempt to decrease it by giving with a ball when you catch it or by flexing at your knees, your ankles, your hips when you land from a jump or fall. A lot of equipment that's used in sports also considers this work energy principle to reduce potentially damaging impact forces. So, for example, the landing pads that are used in gymnastics and in high jump, they increase the displacement during the impact period or the landing as the kinetic energy of the athlete is decreased. The impact force is then decreased because the displacement during the impact period is increased. So it's the same thing with gloves in boxing or with airbags in cars. They're referred to as shock absorbing, but they're actually energy absorbing materials. The work energy relationship is also useful when we examine situations in which no external forces act other than gravity. So in these situations, no work can be done because no external forces are acting on the object. If no work can be done, then the total mechanical energy of the object in question is conserved. It can't change. So just to repeat, to really make that stick, the total mechanical energy of the object is constant if no external forces other than gravity act on the object. So let's think of this principle as it pertains to projectiles, right? From week 5, we're very familiar with projectiles. So we know that gravity is the only force that acts on a projectile. If this is true, then the total mechanical energy of a projectile doesn't change during its flight. So if you think about dropping a ball, just before you let it go, the ball has potential energy, but no kinetic energy. During the ball's fall, its potential energy decreases because its height decreases, but at the same time, its kinetic energy increases as it is accelerated downwards by gravity. So this increase in kinetic energy is exactly matched by the decrease in potential energy. So the total mechanical energy of the ball remains the same as it travels. Okay, let's end the semester on a powerful note. The ability of an athlete to increase the displacement of an object while exerting a force affects their performance in many skills. This means that success requires the athlete to exert a large amount of work on an object. In some sports, excelling requires not just the ability to do a large amount of work, but also the ability to do work in a short period of time. So power is this mechanical term that describes exactly this ability. In mechanics, power is defined as the rate of doing work, or in other words, how much work is done in a specific amount of time. So you can think of power as how quickly or how slowly work is being done. And mathematically, power is defined as P equals U over delta T, where P is power, U is work, and delta T is the time. You can also rearrange this equation to define power as the average force times velocity along that line of action of the force. The unit of measurement for power is watts, which is abbreviated by the letter W, and that represents 1 joule per second. The concept of power is useful in biomechanics for several reasons. Suppose that you have to move a pile of books from one table to another, and you want to finish this task as quickly as possible. This means that you want to maximize your power output. You can take on different strategies to accomplish this task, such as moving the books one at a time or moving the books all at once. The amount of work done to the books will be the same, but the time it takes, and therefore the power output, may be different. So carrying the entire stack at once would require a larger force, and the movement would be slow. Carrying a few books at a time in several trips wouldn't require as much force, and each trip would be quicker. In the first case, you're exerting large forces, but you're moving with a slow velocity. In the second case, you're exerting smaller forces, but you're moving with a faster velocity. The combination of force and velocity determines this power output. So does the larger force in the first case make up for its decreased velocity? Or does the larger velocity in the second case make up for its decreased force? What is this trade-off between force and velocity? We're faced with these similar decisions in certain sports and activities. So how do you choose which gear to use while you're pedaling on your bike? Do you use a high gear that requires larger forces and a slower pedaling rate? Or do you use a lower gear which requires smaller forces but a faster pedaling rate? That's the same as thinking of the books in the previous slide. When you're running, how do you choose your stride length and your stride rate? One clue to answering these questions may come from studying our muscles. Because the power we produce in our movements ultimately comes from our muscles, the power production characteristics of muscles may provide some insight into these questions. So as a muscle's velocity of contraction increases, its maximum force of contraction decreases. So a muscle contracting slowly can produce greater force than the same muscle contracting at a faster rate. The maximum power output occurs at a velocity that's approximately 1/2 of the muscle's maximum contraction velocity. So this would mean that the best gear to use in cycling may not be the highest or the lowest gear, but somewhere in between. The best stride length in running may not be the longest or the shortest, but one that's in between the two. So, to answer our previous question, the best way to move that stack of books may not be to carry them all at once or one at a time, but a few books at once. The best choice of cycling gear, running stride, and strategy to move the books may be the one in which your muscles contract at a velocity corresponding to the velocity of maximal power output. Another reason that power is an important topic in the study of human movement is that it's actually a constraint on human movement. So if you consider an Olympic weightlifter that's performing a clean and jerk movement, the forces that they exert on the barbell and the fast movement of the barbell indicate that the power output of the lifter is quite large, but only for a brief period of time. If the time interval were longer, the lifter would not be able to produce as much power. So the duration of the activity influences the sustainable power output of an individual. A sprinter, for example, can maintain a high power output for only a short period of time, like less than a minute. A middle distance runner's power output is smaller, but it's sustained for a longer period of time. So think of like 1 to 7 minutes. And then a marathon runner's power is even smaller, but it's sustained for a much longer period of time. So that's what this curve is showing you here. It's the relationship between the power output and the duration of the movement or of the power output in human movements. Well, that wraps up the lecture videos for the course. In this last video, we learned about the work-energy relationship and power. I hope you found these videos useful. I know it's not the same as learning together in person, but it is what it is. So here's a look at what's left or what's remaining in the course. So don't forget that your annotated bibliography assignment is due on November 26th before the end of the day, so before 11:59 p.m. You can find all the details about that assignment in the annotated bibliography folder in the content in OnCue. So I also received a lot of positive feedback about the in-person help sessions before the midterm. So I've booked some more time for us to have that opportunity during weeks 11 and 12 because there's no more lecture material for the course. So on Mondays in weeks 11 and 12, I'll be in room 104 of the SKHS building. That's not the same room as for the midterm. It's like a smaller room, but that's all that was available. And then on Thursdays, I'll be in room 101. So that is the same big room that we had for the midterm. And again, these sessions are totally optional. You don't have to come. Drop in anytime that works for you and ask whatever questions that you might have. Or you can also just come to chat about life. I'll be there, and I look forward to chatting with whoever shows up.